Hi, in this series I'll be going through statistics, and before we start, we have to understand some mathematical background before we can apply this math to statistics. While we don't need our math to be the most rigorous, we still need a baseline understanding of certain functions and terminologies to help us move on with applying probability into estimating parameters, which is what we'll study on in statistics. So an introduction will be first that a random experiment is unpredictable. The word random is somewhat of a subjective one, as the experiment could be random to one person and not to another. And how we really define random is not really any mathematical rigor way. It is really when you repeat many times independently under the same conditions, the results have some sort of regularity. So no one's biased to any result. And the probability is the limiting relative frequency of its occurrence as the experiment is repeated many times. So in statistics, we like to take this definition for the probability. While it's not entirely rigorous for mathematicians and is not the one used in analysis, this idea that it is a limiting relative frequency will help us understand statistics easier. So in this course, we'll use a bit of rigorous math and also intuitive, informal way of explaining statistics to make it easier. So I have a series on probability, and I suggest that you can read that up if you want to understand deeper into each how probability is understood. But for now, we will just keep it short and simple and go through some introductory stuff that we'll need to push ourselves forward in the study of statistics. And one thing, of course, we must understand is that we have an experiment, and from an experiment we can derive this thing called as random variables. So for example, you have an experiment where a coin is thrown 3 times and a sequence of heads and tails are observed. Thus, you have a sample space of the following, and you can ask whether how many heads are being observed. So this is a function that defines a rule from this sample space into a real number. And since the outcome is random, the number is random as well. And so in general, we can think of random variable as a function from a sample space to the real numbers. And because the sample space is random, the number produced by the function is random as well. So like I said, we can define the total number of heads with x to describe the random variable. And above this random variable, the number of heads is known as a discrete one, as it can only take on finitely many or countably infinitely many number of values. So it's like 0, 1, 2, 3, 4. So it's like the natural numbers basically. And generally, we can also write the probability distribution by describing it with a probability mass function. And it's basically saying that, okay, so what's the probability that 0 heads appear? That means all the coin toss is tails, so it's like half to the power of 3. And what's the probability that 1 head occurs? So it's like 3 choose 1 times half to the power of 2. Then the other one, 2 heads, 3 choose 2, same thing. And so on. So and then they come with 4 heads because you only throw the coin 3 times. So actually the space that you are confined to is 0, 1, 2, and 3. So this is the probability mass function. And another type of random variable is known as the continuous one. And unlike discrete, where it takes on countably infinite number of values, a continuous random variable can take any number on the real line. So it will be uncountably infinite. For example, the lifetime of an electric component. So that can be any positive real number. And to describe this now, instead of using a mass function which is only applicable to have equal, continuous you cannot have equal because a single point will have zero probability. So instead it's like an area, and for area we need to use integral. So we say that the distribution is represented by some function such that the probability is integral of a to b of f. So f is known as the density. Now we move on to understanding what is expectation, and expectation is basically like your weighted average. So you got mass function which is p1, x1. So let's say we got a very easy example. We got 0, 1 and 2. And 0 takes up 5/6. This is like 1/12 and this 1/12. So it is more likely that the weighted average is closer to 0. And the reason is because you take 5/6 times 0 plus 1/12 times 1 plus 1/12 times 2. Then you see the 1/12 here, they play insignificant to this 5/6. So the weight and expectation for discrete is just taking the sum of the value multiplied by the probability. As for density, because it's an integral, you just need to integrate minus infinity to infinity for x, f, x. So x is like your value, f is your density, then you integrate it. And thus, it can also be shown that if you just replace with a function of x, so this random variable, you replace it with hx, which is now a random variable, it will just be the value at hx times probability, and then here is just hx times fx. Because, okay, so how to understand this is let's just take the discrete case. You got 0, 1 and 2. Now we put into a function called plus 1. So this is 1, 2 and 3. Well, the probability of getting 1 now is still the same as 5/6. So you can see that there's no change in the probability. So the weighted average is just actually the hx times the probability summed together. And variance is defined to be the expectation of x minus mu. Mu is ex, basically, is the expectation, like the mean. So x minus mu is like your distance from the mean, then you square it to have positive distance, then you just take the average of all these distances. That will give you like some idea of the spread of the distribution. And we can actually show that this formula reduces to this, ex squared minus mu squared. And the reason why is you can just expand this out, and by linearity, we can put out into each component and then simplify. And if you take this random variable and minus a constant, the spread still is the same. So it is actually the same as variance x. And okay, so while variance tells you like the spread, we actually use standard deviation to precisely say what is the spread. Because here you square it already, so you need to square root of variance, and this actually measures the spread around the center ex. So another thing that statisticians like to say is that we run an experiment once, x produces a number, so x gets one number, maybe like 2, and this is known as the realization of x. So let's take another example to familiarize ourselves with using continuous density functions. So let's just find the density of x equals to z squared. So z is some normal distribution, 0, 1. So we want to find x, the distribution, it equals to probability x less than or equals to x. Then this is x is what? X is x squared. So it's actually the probability of minus x square root x to square root x. And this can be reduced to phi of square root x minus the phi of minus square root x. And so we can differentiate this to get the density function from the CDF. So differentiating, we get that x to the power minus half times phi of square root x. And evaluating the last expression, we obtain this. And we recognize this to be the gamma distribution by making use of the principle of general utility. And suppose that two densities are of the form this, and since they integrate to 1, K1 and K2 must be the same. Now comparing the form of fx to the gamma, we see that it is just the alpha equals to half. And so this density is also known as the chi-square density with degree of freedom 1, and we'll dive deeper into that later on in our series. For now, you should just understand that this z squared is actually like a gamma distribution. So it means normal squared, the variable original standard normal, you square it. This is still a random variable and is following a chi-squared distribution. Other things that are important is the law of large numbers, and this will be very useful in estimation later on. And it says that the mean and variance of the realizations are this. So that means you got so we got like x1, x2, x3. So these are the different, you repeat the experiment many times and you find the mean. And the variance is as follows as well. The law of large numbers says that for any function h, as the number of realization r goes to infinity, then this will approach ehx. So it becomes the expectation of the original distribution x. So what does this mean? This means that x bar will approach ex and v will approach variance x. So you can actually use x bar and square root v as a rough estimation of the center and spread of x once you have enough realizations. This helps in, well, one example is in the Monte Carlo approximation method where they approximate this hx to be approximately this function. And by the law of large number, this approximation becomes good as r goes to infinity. So it's a good approximation. Another thing that we'll need in statistics is a joint distribution, as many of times in statistics we have many different types of random variables and we want to see the interaction between the two. And so a joint distribution, the cumulative one, is as follows: is the probability of x less than or equals to x, comma y less than or equals to y. And it's basically like a rectangle, and then so x less than a, x, y less than b, and then you just shade it. And so a random experiment can produce two random variables, and we want to see how their probabilities are correlated to each other. So their joint distribution can be described by the mass function as follows, and their density is just a double integral. For expectation, you just take a double sum, and likewise for continuous case, you just do the double integral. So you can see the formula is the same, but now you just have this double, because now you have two random variables. So what do I mean by the interaction between the two random variables? For discrete random variable, we just see the joint frequency function as the following: the probability of x equals to x and y equals to yj. So for example, you got the total, your x is the number of hits on the first toss and y is the total number of hits overall. We see that x can either be 0 or 1, but y can be 0, 1, 2 or 3. And for also, let's say x is 0, then y is 0, that means the second and third must be both 0. And if x is 1, then y is 0, then that's not possible because y is the total number of hits, so the probability must be 0. And this is like your joint frequency. Like what's the chance that x is 0 and y is 0? What's the chance that x is 0 and y is 1? So on. And suppose we wish to find the frequency of y from the joint frequency, it's very straightforward. So basically, there's two cases here, and by the law of total probability, you just need to add them up. So instead of splitting into two, you just combine them. So it's 1 over 8, 3 over 8, 3 over 8, and 1 over 8. So the probability of y is 0 is 1 over 8, and so on. Same for x, you just need to sum it horizontally. So the marginal frequency is the addition of, let's say you want to find the x, then it's addition of all the y's cases. And this leads us to an example of a very frequently used multinomial distribution. And it's basically a generalization of the binomial. And suppose we have n independent trials, one of r types of outcome. So in binomial, there's only two outcomes, failure or success. But now you have r types of outcome. So let's just say you have a probability that n1 all the way to nr. Then it will be just n choose n1 choose times this nr. Then you times the probability. So this is the multinomial coefficient. And the marginal distribution for any particular ni can be obtained by summing the joint distribution of all the other ni on j's. But then you recognize that it will be quite tough, but you actually realize that ni is just a binomial. So you can just use the binomial formula. So it's not too hard. As for the continuous case, it's very similar, but now everything is integral. So if, let's just say we have an axis here, and xy is, you have some a probability space a here, where xy lies inside. So xy is all this. So it's just the integral of the area a of the density function dy dx. And if you want to find the cumulative, it's just minus infinity x minus infinity to y. And by the fundamental theorem of multivariate calculus, finding the density now is just differentiating this with respect to x and differentiating this with respect to y. So it's partial x, partial y. From this, it follows that the density function can be known as the marginal if you just different. Then you find this already. Then you take this and you integrate. Okay, you integrate with respect to y. So it's like summing it. And another thing we like to note is that when you have two, so we know how to calculate the variance, we know how to calculate the expectations. The thing now we have to note is there's this thing known. So what is this variance? This variance is known as the covariance between x and y. So it's like how does the spread relate between the two x and y. And this covariance is the expectation of x minus the mu for x times the y minus the mu of y. And with this expectation, we can expand out and see that it reduces to e of xy minus mu of x, mu of y. How to find the e of xy? Well, it's the double integral of xy f xy dx dy. And the covariance of xy is of course symmetrical to the covariance of yx. And the covariance of x and x is actually just the variance of x. Because if you sub in here as x, this is x squared, and this is mu x squared. So you see the formula are equal. And we also see covariance is bilinear, because if you just take the covariance of w comma ax plus by plus c, it takes out the a, so it's like a covariance wx plus b covariance wy, and the c, because it's constant, the covariance of that will be 0. There's no spread. So from this formula, you can deduce that the variance of ax plus by plus c, which is just summing this as ax plus by plus c. So you sub this as ax plus by plus c and expand out again. You should get is a squared variance x plus b squared variance y plus 2ab covariance xy. So That's all for this introductory in probability. First, we'll dive deeper into applying it in the subsequent videos where we build up our knowledge on probability first. So that's all for this video. I'll catch you again. Please like, share and subscribe if you have enjoyed this video. Leave any comments in the comment section and I will answer them, and I will improve on any feedback. Thanks. Bye.